the session in the afternoon, and that's going to be by Amy Fagan, who is a recent postdoc at LPI, and she is going to be speaking to us about trapped argon-argon closure ages of lunar regolith breccias 3.9 billion years ago to present. Take it away when you're ready, Amy.
With the talk of explaining a little bit about what a regolith breccia is, particularly as I noticed that a lot of the talks for the forum so far have been modeling. There have not been very many that have focused on the samples. So a regolith breccia is something very simple. It contains at least one regolith component, such as glass spheres, which I show here in the figure on the right. My cursor doesn't seem to be working right now, but you can see any of those circles. Those are those glass spheres. Other components that you find in a regolith breccia are glutinate and a high solar wind content. And what's really interesting about these regolith breccias is that they serve as recorders of the lunar surface history. We see events such as pyroclastic deposits, particularly in Apollo 15 and Apollo 17 regolith breccias, as well as the regolith samples themselves, the soils. A lot of interesting work has been done recently on those, looking at the volatile content. We also see evidence of impact events. So we see impact melt clasts in these regolith breccias and also melt spherules. And recently, these have been seen in the past, but recently Katie Joy and others in 2012 looked at the type of impactor relics that we see in the Apollo 16 ancient regolith breccias. And there is some variation. It appears that there's variation in the type of impactor hitting the lunar surface and really the whole Earth-Moon system at different time periods. And the time periods were ascertained by looking at these the regolith breccias and the closure ages. And finally, we see the trapped gas values in these regolith breccias are recorded. And this is really what I'm going to focus on today, particularly with the argon-40 and argon-36 values. So these values are different for different time periods throughout the lunar surface history. At a time period approximately greater than 3.7 billion years, this is during the basin-forming epoch, we have high mantle heat flow. This is largely due to the fact that we have more radioactive elements such as potassium-40. We have partial melting and degassing. The potassium-40 is radioactively decaying to argon-40, and this is being degassed. We also have a high crustal heat flow. A lot of this is actually due to the high projectile flux. It's because this is the basin-forming epoch, we're having these thermal pulses. And this is, again, causing this degassing. And you see all these big white squiggly lines saying degassing to lunar exosphere. And finally, on the surface of the moon, we have the lunar regolith. The regolith breccias at one point in time were regolith, and this was exposed to the solar wind. Argon-36 is implanted into the regolith by the solar wind, and this argon-40 that has been degassed into the lunar exosphere is actually re-implanted into the regolith, and this is what we call trapped argon-40. And so the trapped component is the argon-40 that did not form in situ from radioactive decay. This has been re-implanted. At younger time periods on the lunar surface, we actually have a slightly lower argon-40, argon-36 ratio. This is due to a lower mantle heat flow, which is due to the fact that we have less potassium-40 and other radioactive elements. So if we have less potassium-40, we have less argon-40 that is being degassed. We also have a lower crustal heat flow because we don't have as many thermal pulses as one component of it. So we're also degassing less argon-40. So whereas the first slide you saw the big white squiggles, now you just have one tiny little white squiggle showing the degassing. But we still have regolith sitting at the surface. And it's still being exposed to the solar wind. We're still getting this argon-36 and argon-40 component. But because less argon-40 is being degassed, there's less that is being re-implanted into the surface. So this is why we have a lower argon-40, argon-36 ratio at more recent time periods. The great thing about the difference in these ratios is that we can use it as an antiquity indicator for when these the regolith components of these regolith breccias were once on the surface of the moon. And this is what we refer to as the closure age. This is the time period when the regolith itself was shielded from further solar wind input. And this could be from a basalt flow going over the surface of the regolith. It could be from ejecta from an impact crater or even a landslide. And this closure age uses the trapped argon-40, argon-36 ratio. And it's actually an equation that was modified by Katie Joy and others in 2011 after Euster et al. Equation in 2001. And so this is the equation that we use to calculate what the closure age is and determine when these regoliths were closed off from further input. So here I show a plot of some work that has been previously conducted. On the x-axis, you see closure age from approximately 4 billion years up to present. On the right axis, on the right side, we have Apollo 16 data, which was conducted by Joy et al. In 2011. These are the Apollo 16 regolith breccias. And then more recently, for LPSC this year, we examined 25 of the Apollo 15 regolith breccias. So the point of this work is actually to expand this data set. We have Apollo 16, we have Apollo 15, but there were several other Apollo missions, so we wanted to look at those and see if there was any sort of variation of the closure ages between these missions. So we have about 78 regolith breccias that we examined, and this is by extracting argon-40 and argon-36 data from the literature. But one of the important things you have to keep in mind is that there are more regolith breccias actually out there than what we have in this study because we are constrained by what is actually already in the literature. Another thing to keep in mind is that 6 of the regolith breccias actually generate negative closure ages. This is actually an artifact of the calibration. They have very, very low ratios, and we don't actually consider these further, so we're going to eliminate those, and we hash it down to 72. But 72 is still a good number. So here's a plot of all of our data. Again, on the x-axis, we have the closure age, and on the y-axis, we have the different samples from their different stations, sites. I want to focus here just a little bit on Apollo 16. This is samples from this site generally have the oldest closure ages. However, we also have some from Apollo 14, which is the oldest Mare basalt unit that Apollo directly sampled, and Apollo 16 obviously is the ancient highlands. Both sites also have some samples that have younger closure ages, but in general, most of them are greater than 2 billion years. In contrast, Mare sites that have younger Mare generally have closure ages of less than 2 billion years. You'll see some from Apollo 15 that are greater than that. I'll go into that in just a minute. And then we also have a full range of lunar meteorites. These obviously were not collected by the Apollo astronauts. We don't really know where they came from on the surface. And so these actually give us a global distribution of closure ages on the lunar surface. I'm going to quickly go into Apollo 15 and Apollo 12 because those are really interesting. I think I've highlighted here the 4 oldest samples from Apollo 15. These are the only ones that are older than 2 billion years old. And these 4 samples were collected on the rim of Spur Crater along the Apennine front. And I've shown a picture here of Spur Crater with Hadley Rill in the background, and I've put a dashed line around Spur Crater. It's kind of hard to see. One of the interesting things about these samples is that they are rich in green glass. The green glass, at one point in time, we thought the green glass might be actually affecting the closure age and causing it to have this high ratio. But there are some soil samples that also have extremely high glass content that have lower closure ages because they have lower ratios. These samples also, though, were collected along the Apennine front, so along old material, and that could also be affecting this, this closure age. So this is likely a bit of a mixing effect. And then, real quick, I want to go over Apollo 12, which has been known in the past, has been shown that it has some creepy samples, with creep standing for potassium rare earth element phosphorus rich. Apollo 12 site is actually on one of the rays from Copernicus crater, and some of the samples from Apollo 12 have been suggested to have actually originated from the Copernicus impact event. One of these regolith breccias here, highlighted in blue, is one of these creepy samples. You can see that there is actually quite a difference in the age between, the closure age between the non-creepy sample and the creepy sample. And if you can tell, the creepy sample closure age is around 0.8 billion years, and the age of Copernicus is around 800 million. So this is also showing us that we have inputs from fairly far away. Marvin et al. In 1971 looked at the Apollo 12 site, and although about 50% of the regolith components and input come from about 3 kilometers away, 95% of the regolith likely comes from 100 kilometers. Well, Copernicus is about 400 kilometers away. So even though we think that a lot of the regolith components can come from fairly close by, we clearly do have some effect from elsewhere. And this is indicating that we actually have mixing probably going on with a lot of the Apollo stations. Particularly with Apollo 17, we see this also has green glass-rich soil samples that were also collected along a mass beach. There's a lot going on in these samples that we might not have really focused on in great detail for a while, and I think we should go back and look at them. So just to run through a quick summary, because the argon-40, argon-36 ratio has changed over time and is recorded in the regolith breccias, we actually can calculate closure ages of these samples to determine when they are on the surface. And from the 72 regolith breccias we have here, we have a fairly complete record of the surface history, ranging from almost 4 billion years ago to close to the present. And finally, we do have quite a bit of mixing affecting the closure ages of these samples. And although we have a fairly complete record of the surface history, we do need more samples to enhance the data set. These can be from human and robotic sample return or collected meteorites. This can also fill in the temporal gaps as well as the geographically and geologically diverse sites. And I see that I have 19 seconds left. So with that, I'm going to stop.
Great, thanks. So there's actually a fair number of questions that we have for you in the chat window.
In 12 seconds, right? 12 seconds.
In 12 seconds. We have, you're the fortunate one to end the session, so we have a little bit of time to answer some questions. You're lucky that way. First question is, considering that the moon does not have a constant and well-known exosphere, how secure are you on the constant evolution of the argon-40 to argon-36?
Okay, sorry, I'm rereading your question, Vera. On the constant evolution, I have to get back to you about that. That was mostly trying to give a schematic diagram of where the argon-40 and where the argon-36 comes from. I think it's highly likely that it did vary, at least to a certain extent. I cannot quantify that right now. But you had a second part of your question, too.
Okay. She actually clarifies this later on, slightly down, says, basically all I want to know is how do you interpret and clean, quote unquote, the data from the possible sources and losses of argon-40?
So when you mentioned the loss of argon-40, do you mean so when you actually have an impact event that will form the regolith breccia and bring it up to the surface? Or, oh wait, she has another question. Vera, it's a lot of what we're doing is I did actually look into the porosity, and we don't see any sort of at least systematic difference with the porosity versus the closure age or the argon ratio. Because I remember you brought this up at LPSD and asked about the porosity and the density, and I can't really comment too much on that right now. It's just that we don't really see much of a difference with the porosity of different samples and the argon ratios at this time.
Okay. Sonia from MIT asks, what's the uncertainty in general of trapped argon ages, i.e. plus minus number of years, factoring in some of the uncertainties that Vera was talking about?
work of McKay et al. In 1986, they looked at Apollo 16 regolith breccias and did quite a bit of work on the argon ratios, and they had it was almost a 30% error in the trapped argon. Now there are other studies that have used different methods to calculate what the trapped ratio should be that I believe have much lower errors, but it kind of depends on which samples you're looking at, which papers you're using. It does vary, but if you had a 30% error on the argon, the trapped argon ratio, your age might vary from 2 billion years to 1.6 up to 2.15, 2.2. So there is some variation, yeah. But it depends on which data set you're using.
Great. And the last question's from Bill Bakke. He says, "Hi, Amy, nice talk. I was curious whether your method could be used as a means to get the age of distant craters via closure ages and nature of terrains. Your example of Copernicus was neat."
Thanks, Bill. Bill, I remember at LPSC you actually asked about if Aristillus and Autolycus could be mechanisms by which we could get some of the Apollo 15 regolith breccias. And actually, those impacts themselves were about, I think, 150 to 250 kilometers away. So it's highly likely, I think, that you do get some input from them. I think you have to try to really delve into the individual petrology of the samples if you're going to try to determine where some of these particles came from. And I know that some of that work has been done. Ryan, at least on other samples, Ryan Ziegler in 2006 looked at some of the salt class in Apollo 16 samples and estimated, based on Clementine, I think, where the samples could have come from. The closest MARI site to Apollo 16 is about 220 kilometers away. So even with that, even if you're working on that 95% of the regolith is sampling an area of 100 kilometers, clearly you're getting input from elsewhere, as shown by Copernicus, and then also by the Apollo 16 MARI salts that come from at least 200 kilometers away. So some of that work has been done. I'm not sure how much you can relate the closure age and actually nailing down which sample, or excuse me, which crater they could have originated from. But if we do have samples from a particular site that are anomalously young or anomalously old, then that does certainly indicate that there's something going on, particularly with what we've seen with the Apollo 15 regolith breccias with the green glass. Also the Apollo 17 soils, the oldest soils, also have a lot of pyroclastic glass in them as well. So those definitely require you to go back through and see really what's going on.
Great. Fantastic. Thanks so much, Amy. Appreciate it. And that concludes our afternoon session for the second day Lunar Science Forum. Just as a quick reminder, the sessions do start tomorrow morning